Hello everyone, welcome to lecture CHE 446, Process Control. What we want to learn today is everything about how to derive mass transfer and heat transfer equation, heat transfer balance equation, and how to find transfer function for this system which has um, two inputs, two outputs. This is a heating for a continuous flow water. Also we have pump on the outlet flow rate. This system is the center point of our study for today, which is a heating for a continuous flow. So the flow, liquid or water, comes inside the system with the temperature of Ti and mass flow rate of omega I, and leaves the system with temperature of T and mass flow rate of omega. We have heater in the system which releases energy of Q to the water actually inside the tank, and we have pump which has effects on the elevation of water inside the tank. Also we assume that this tank is well mixed, which means that the temperature of liquid leaves the system is the same as the temperature of the liquid inside the tank, and the temperature inside the tank is homogeneous. And also we assume that the area, cross-sectional area of the tank is constant, and also density and heat capacity of liquid is constant as well. What is the objective of this question? Objective is to find the four transfer functions between two inputs omega or omega I and Q, and two outputs H and T. We want to write it based on omega. And the first thing or first equation that comes to our mind to write is the mass transfer balance equation, mass equation. So let's start with writing the mass transfer equation. Total mass balance is actually can be written as change to pen. So mass balance, as you know, can be written, I change this to red, and you can see exactly, and then mass balance is actually changes of mass based on time, which can be written as actually D rho density multiplied by V, which is A multiplied by H, changes based on time, and is equal to mass flow rate in minus mass flow rate out of the system. Knowing that rho A is constant, we can simplify equation and write it as dH to dt equal to 1 divided by rho A, this one is rho A omega I minus omega. Let's call this equation as equation number 1 because we need it later. The next equation is that is easier to write is total energy balance. Okay, total energy balance. Let's write it as changes of energy, which is actually D changes of energy based on time, and energy is mc delta theta, so we will see m, which is rho multiplied by volume, which is A multiplied by elevation, heat capacity, multiplied by heat capacity, and T minus T reference. Why I select T? Because I assume that system is well mixed and the temperature of flow which leaves the system is equal to the temperature of liquid inside the tank. So the energy changes of energy of liquid inside the tank, I use the temperature of outlet of the tank for this part of the equation. And then I will say equation energy in to the system is omega I C, which is heat capacity, T of flow inside the tank, as can be written as Ti minus T reference minus energy out from the system is omega C, heat capacity of liquid, T outlet temperature minus T reference plus Q of heater, because heater releases energy to the system. We also assume that T reference is 0, so we can eliminate T reference from our equation because we assume that T reference is equal to 0. We can also, actually knowing that rho A C is constant, we can just pull them out of this operator, derivative operator, and we will have H and T inside the operator. But we know both H and T are variables, so we have to use the chain rule for derivation, and we will have rho A C multiplied by H dt, changes of temperature based on time, plus T dH by dt, and then right hand side of the equation is omega I C T I minus omega C T plus Q, and also we can simplify it more because we have dH by dt here, which is the same as equation 1, so let's substitute that. We will have rho A C multiplied by H dt plus T multiplied by 1 divided by rho A omega I minus omega equal to right hand side of the equation. We can expand this more and we will have rho AC H dt plus rho AC T divided by rho A. So rho A can cancel rho A, so you will have CT omega I minus CT omega equal to omega I CTI minus omega CT plus Q. Then we will see that CT omega cancels here with omega ct. So the simplified version of equation would be dt by dt, which is time, equal to 1 divided by rho AC multiplied by omega I C Ti minus omega C, actually omega I CT plus Q divided by H. We will call this equation number 2. And let's see, equation number 1 that we have is linear, but equation number 2 is non-linear because we have a multiplication of two variables. In order to further do the further solution, we need to linearize this system, which we will discuss in the next lecture. But before that, let's see the degree of freedom of the system. We know the number of equations that we have in this system is 2. So this is the number of equations in the system. But the number of variables in the system is, let's count it. The number of equations is 6. Why? Because we have t, we have omega I, ti, and we have h, we have q, and if you look at equation 1, we have omega. If you count so if you count the number of variables, we'll have 1, 2, 3, 4, 5, 6. So the number of variables that we have is 6. Degree of freedom would be subtraction of number of variables minus number of equations, which is 4. What does 4 mean? 4 means that we must identify 4 input variables to the system that can be specified, because in order for equations to have a unique solution, we should have the same number of defined variables and the same number of equations. If we select H is here and T, we will cover two states. So H and T are output variables on the left hand side of equation 1 and equation 2. The other two variables, so we already defined 2 of these 4 degree of freedom. The other 2 can be input variables but manipulated variable 1. So if I select Q, it helps us to control T, and also if I select omega I, it helps us to control H. So I will select omega I and I will select Q as the other 2 variables that I can decide to select. Okay, in order to go further in our solution, we need to linearize this equation 2, and please watch the second video for this for solution of this question. Thank you.